Okay, so where we left off there, sort of in lecture, was we were talking about really sort of physical changes, and we talked a little bit about chemical changes. But a reminder, as we were talking about, again, physical changes is where we start with something, and what we end up with is fundamentally the exact same thing. There's no real change to really the substance itself. Now, that's very different for a chemical change. Usually, chemical changes involve chemical reactions. And in a chemical change, we really do form something that is fundamentally different from what we started with. So, for example, if we take some hydrogen gas and we take some oxygen gas, and we'll make some water here. And water is fundamentally different than the hydrogen gas and oxygen gas it comes from. And as we talked about, you could take this water and you could do all kinds of physical things to it, and you'll never get back, the hydrogen gas or the oxygen gas, which we know when we do make, for example, pasta, like I think it was a picture earlier. When you boil pasta for the water to make the pasta, um, what we get is not hydrogen gas or oxygen gas back in that process. Otherwise, we would never get to the pasta part because it would probably explode. But what we get is basically just water going from liquid to steam and so forth. So we have fundamentally changed it into something new. Rust is another example of that. For example, you basically, for rust, you need some iron metal, you need some oxygen gas, a little bit of moisture, and you'll make iron 3 oxide, which is basically rust. Spell that right, rust. And the difference between the iron and the oxygen here is when we started, they were separate from each other. Here, they are basically chemically united together. And again, you can do whatever you want with rust. You could put it in the freezer, you could boil it and all that kind of stuff. You're not going to get the iron metal back. You're not going to get the oxygen gas back through any type of physical means. So when we do a chemical change, what we form is something that's new, and you can't get back what you originally started with by any type of physical means. You can definitely take water, for example, and run an electrical current through it and make hydrogen gas and oxygen gas come back. And that is also a chemical change. So this would be an example of a chemical change as well. Again, making the hydrogen gas and oxygen gas, you can't get back the water through any type of physical means. Again, if you take the hydrogen gas or oxygen gas and just put it in the freezer, you're not going to magically form sort of water and stuff like that. So physical change, we start with and end with, same thing, may just appear different physically. Chemical change, what we start with and what we end up with are fundamentally two different things. And again, you cannot get back your original substance by any type of physical means. Any questions on that there? Here's just a table from your book, again, of some examples of physical and chemical changes. Again, on the left-hand side, we see things like boiling point, which is a physical change. We see copper can be drawn into wires, a sort of physical, sugar dissolving, and chemical changes. The piece of wood burning, like I might have mentioned earlier, rust forming. When we talk about a chemical change, we're also talking about sort of the resistance of something to go through a chemical reaction. So how something does react in a chemical reaction and how something resists a chemical reaction is sort of a chemical property. And here's just a summary table, what we talked about as well. Again, the differences between physical and chemical. And again, that main difference being, one, we're really not fundamentally changing what we start with, which is a physical sort of process, while a chemical, again, we are definitely sort of fundamentally changing what we started with. So if we look at some examples here, if ice does melt by the sun, that is a physical change. Again, if it melts to liquid water is still H2O. Ice is H2O. It is still fundamentally the exact same thing. Same thing here with our copper. Copper is a shiny metal That's really a physical characteristic, right? Observation type characteristics like color, appearance, uh, boiling points, melting points, states. Paper can burn. That is a chemical property. Again, the ability to react. When we burn something, it obviously goes through a chemical change, or the ability to resist, sort of a chemical change. A silver knife tarnishes. That's also a chemical change. That's basically silver and sulfur coming together to make silver sulfide, and that gives it that sort of tarnish type color that we typically see. A magnet removes iron particles from a mixture. That is basically a physical type of property. That's also a way that you could, separate out something, like if you had sand and pieces of metal in the sand. Kind of like filtration. If you took a magnet, it's going to basically, maybe not that far up, but it will hop out the metal pieces from the sand. And again, that's just a physical sort of separation that's occurring, very much like what we talked about with filtration. Any question on any of those there? So each of these physical or chemical. We have burning of a candle. That is going to really be a chemical change. There's lots of, obviously, perhaps some chemicals in the wax besides the wax melting. It burns away and there's not really wax left. It's up on the bottom, but there's usually some chemicals and stuff in there as well. Ice melting on the street. Again, ice melting going from solid to liquid. That is a classical physical type change. Again, going from solid to liquid to gas or back and forth. Those are all very common physical changes. If we toast a marshmallow, right, that's going to be a chemical change. When we eat the marshmallow, also more chemical changes occurring. Cutting a pizza, that is a physical change, right? It's still fundamentally still a pizza and stuff like that, no matter how you cut it. If you do the sort of square cuts or the round cuts and stuff like that, the wedges, that's still all pizzas and stuff like that, just different shapes. And obviously, iron rusting on cars, like we were talking about, is basically a chemical change. Any questions on physical changes, chemical changes? Obviously, you need to be able to identify a physical change versus a chemical change, and again, what the differences are between them. Okay, then we're going to actually talk about temperature next, and we're talking about how to calculate temperature, some of the different temperature scales that we deal with in chemistry. And I might have touched upon it earlier, but in terms of temperature, there's really kind of three scales we use: degrees Celsius, which is commonly used in science; degrees Fahrenheit, which we commonly use to kind of get our temperature and all that; and a very important sort of unit and temperature is K, capital K, which is Kelvin. And in chemistry, as we'll see, usually Kelvin, we see a lot. Most times that you need to use a temperature value in chemistry is usually in Kelvin. Degrees Celsius also, is oftentimes given. Probably outside of this chapter, probably won't run too much into Fahrenheit, especially in chemistry. Usually degrees Celsius or Kelvin are the two most common sort of units, and mostly Kelvin is used. And that's also a difference is one is degrees Celsius, one's degrees Fahrenheit, but there is no degrees here with Kelvin. So we just say, 273 Kelvin. We don't do degree sign or anything like that with Kelvin. So temperature really is a measure of how hot or cold an object is compared to another. Heat does transfer from hot to cold. So when we're talking about sort of heat being transferred, it goes from hot to cold. So the guy that's warmer cools down. The one that's colder warms up. If they happen to be sort of in an insulated container, they probably will end up at the same temperature, kind of halfway between the two temperatures that they started at. We use a thermometer to take temperature measurements, and it's an equipment just like we talked about in chapter 2 when we talk about measurements. You typically want to look at the scale and try to figure out what does each marking usually represent. And I would say probably on most temperatures, most thermometers, when you look at the scale, for example, we have 11, we have 12, and so forth. So usually you could go to like 1 decimal place on most cases. And again, you should always look at the actual thermometer before you do that. But you usually could take the reading in most cases to that first decimal place when you do take it. So here's sort of the differences on the 3 temperature scales: our Fahrenheit, our Celsius, and our Kelvin. And really how we get sort of the conversions between the different temperature scales is really looking at the difference between the freezing point and the boiling point of water. So the freezing point of water on all 3 scales, the boiling point of water on all 3 scales. For Fahrenheit, it is 32 degrees Fahrenheit and 212 degrees for the boiling. For degrees Celsius, 0 degrees Celsius for freezing point of water, boiling point's 100 degrees Celsius, and 273 Kelvin for freezing, 373 Kelvin there for boiling. The differences between freezing and boiling on the Fahrenheit scale is like 180. Difference between freezing and boiling on the Celsius is 100. Same thing here. It's 100 difference there. And that really is how we get our conversions to go from one temperature scale to the next. So let's talk about officially how to sort of do that. If we want the Fahrenheit and temperature scales, what we see again, that difference between the boiling water and the freezing water is about 100 degrees on the Celsius and about 180 on the degrees Fahrenheit. So to calculate the temperature in Fahrenheit, we take 1.8 times the temperature in Celsius and we add 32 to it. So this is the formula that we use if we are given Celsius and we want to convert that temperature to degrees Fahrenheit. We also can rearrange this and solve for degrees Celsius. That would be the temperature in Fahrenheit minus minus a 32 divided by 1.8. And that would be how you would go from Fahrenheit to Celsius. So again, these are 2 important sort of equations. You probably won't use a ton of these guys here outside of this chapter, but these again is the way you can do that. This is also the 1.8 is really the 9/5 that you might have learned when you were younger as a way of converting temperature. Again, if you take 9 divided by 5 on your calculator, you get basically 1.8. That 1.8 is really based on this 180 degree difference between the freezing point and the boiling point that we got going. Any questions on that there? So again, those 2 you should know. It won't be provided for you. So those 2 formulas, make sure to put a star on it. I think we'll see it coming up here in a slide again. Just to go through what we just talked about, water is, what is the temperature in which water freezes? It is 0 degrees Celsius. And what temperature will water boil? It will boil at 373 Kelvin. That's the boiling point on the Kelvin scale. These are not the boiling points. And how many Celsius units are between boiling and freezing? Again, in Celsius, the kind of difference between boiling and freezing is 100 sort of units between those. And again, that's really what leads us to our 2 equations that we just talked about. And that's these 2 equations here. And again, you do need to know these, and outside this chapter, you might not use them all that much, but you definitely do need to know them. But let's talk a little bit about sort of significant figures and temperature. So there's sort of a general rule when we talk about significant figures and temperature. And what we're talking about is when you do just a temperature conversion. So if you're just doing a temperature conversion, which basically means you're taking it, for example, from degrees Fahrenheit to degrees Celsius, maybe you're going degrees Celsius to degrees Fahrenheit, maybe you're going degrees Celsius to Kelvin. If you're just strictly only doing that conversion there of going from, excuse me, going from one temperature scale to the next, not doing anything else with it, we don't really follow, in terms of significant figures, the really strict rule on significant figures. So what we try to do is when we give the answer should look like the original value. So the answer should look like the original value. And what I mean by that is, let's just say we were going to convert 32.5 degrees Celsius to degrees Fahrenheit. If we were going to do that conversion, we would use this equation here, which is going from Celsius to Fahrenheit. We would take the temperature in Fahrenheit would equal 1.8 times 32.5, and then we would add a 32 to that. Let me get my calculator because I just made up a number there. So we got 1.8 times 32.5. We're then going to add a 32 to it. That is going to give us 90.5 degrees Fahrenheit. Now, in terms of significant figures, in this particular case, it came out okay. But in terms of significant figures, what we would want to do is, because our original value went to the first decimal place, we would want to do our converted value to the first decimal place. Now, if we did, say, just 32 degrees Celsius to degrees Fahrenheit, we would do the same calculation here. And let's see what we get when we do this guy. We end up with 89.6 when you punch it into your calculator. Now, when we look at our original value, it actually was a whole number, no decimal points. That means when we do our answer, we technically would want to roll it to no decimal points. In this case would be 90 degrees Fahrenheit. So this is really sort of specific for temperature conversions. Basically, we want to make the converted value look like the original value. The reason why we do that with temperature is really because of this part right here. When we use that part right there, some people use 1.8, some people use 1.80, some people use 9/5, which is a fraction. So there's a lot of sort of variance you could get depending on sort of how you look at it and what value you use. So the general rule for temperature conversions, and only temperature conversions, again, is whatever that original number looked like, that is what you should make your converted number look like. If it went to 2 decimal places to begin with, you should convert it to 2 decimal places as well. Went to a whole number like we did there, you want to convert it to a whole number as well. Any questions on that there? So if we look at this one here, again, we have 21. So we would put it into our formula here. And the temperature in Fahrenheit would be 1.8 times our 21 plus a 32. And same idea here, 1.8 times 21 plus 32 gives us 69.8 degrees Fahrenheit. Again, we go back to our original number here. It is to the whole number. So we would want to round this to 70 degrees Fahrenheit. Question on that particular conversion there. So again, those two conversions is something that, like I said, probably outside this chapter, you might not use all that much. The one that you really will sort of use the most is the next conversion we're going to talk about, which is Kelvin scale. So when we're converting to Kelvin, we basically do this a lot in chemistry. We basically go from degrees Celsius to Kelvin. That is a conversion we do over and over again. Again, almost all chemical sort of formulas that involve temperature definitely usually needs to be in Kelvin. We'll see that when we get to gases. You definitely need to make it in Kelvin. So the Kelvin scale used to be called the absolute temperature scale. And basically, to convert to Kelvin, like it shows on the bottom, you take the temperature in Celsius and you pretty much add 273 to it. So that 273 is an important number. That is typically what we add. The actual true number is 273.15. Virtually nobody, and if you want to, you can, but virtually nobody uses the 0.15 part of the number anymore. But if you want, you could do the 273.15. Most of the time, people don't do that because it typically will get rounded off anyways. So 273 is a perfect number to use. But in case you do see it somewhere, the actual true number is 273.15. Also means that if we have Kelvin and we want Celsius, we would take the temperature in Kelvin minus 273. So these two formulas are really important. Out of all the ones we saw in terms of temperature, this guy right here is probably the one that you will use the most. When we talk about absolute zero, that is, sort of the lowest temperature. That represents minus 273 degrees Celsius is what is sometimes referred to as absolute zero. Again, the other important part is, as it says here, no degree symbol. So we would just say, again, 273 Kelvin or 300 Kelvin, and that is basically what we would do. Any questions on that? And again, out of all the temperature conversions, this is definitely the one that we will use a lot in most of the remaining chapters. Again, you may use some of the other ones, but most likely you'll do this. Now, something that sometimes comes up is like, hey, if I want to go from degrees Fahrenheit to Kelvin, sort of what is the path? So the path to do that is you need to go from degrees Fahrenheit to degrees Celsius and then to Kelvin. So you kind of have to do that whole path there if you're going from one spot to next. We really do the same thing here as well. So, if our Celsius was to the first decimal point, we would take the Kelvin to the first decimal point. If our Celsius was, again, no decimal points, we would take the Kelvin to obviously no decimal points either. Any questions on that there? All right. So why don't you take a second here and see what you come up with. What is the normal body temp? What is normal body temperature of 37 degrees Celsius in Kelvin? And while we're at it, why don't we also do degrees Fahrenheit? So take a minute or so. Okay, I see some answers rolling in. So let's take a look. So we'll start with the Kelvin. So again, to convert us into Kelvin, we're going to take the temperature in Celsius. And again, 273 is our number. Try to remember that number. I've seen people use all kinds of weird numbers. That means we would end up with 37 plus a 273. And that is going to give us 310 Kelvin. Again, no degrees listed there. Any questions on that calculation? Again, whole number here, whole number on our answer. So that's where we'd want to kind of end it. Also want to do temperature in Fahrenheit. So again, the temperature in Fahrenheit is 1.8, temperature in Celsius plus a 32. That would give us 1.8 times 37 plus 32. Going to get us 1.8 times 37 plus 32 gives us 98.6 degrees Fahrenheit, which is our normal body temperature. And again, here, technically speaking, because this is a whole number, we would round this to 99 degrees Fahrenheit to make it look like our original number. Any questions on either of those two conversions? Then let us take a look at this one. You want degrees Celsius, and why don't we also do Kelvin as well for this guy? So take a minute or so. Okay, I see some answers coming in on the first part there. So again, our temperature in Fahrenheit is 1.8, our temperature in Celsius plus a 32, which means our temperature in Celsius, temperature in Fahrenheit minus 32 divided by 1.8. In this case, the minus is important, so that's going to be minus 15 minus a 32 divided by 1.8. And we would end up, obviously, in this case with, I believe, what everybody was punching in there, we would end up with minus 26.1111, a whole bunch of ones, degrees Celsius. Again, here, based off of our original number being a whole number of minus 15. So then we would want to take this to the whole number, which would be here, and that would give us minus 26 degrees Celsius. So again, specifically for temperature, that sort of general will make the answer look like the original answer. Also, because we now have it in Celsius, we could figure out Kelvin because it is the temperature in Celsius plus a 273. Again, here the negative is important. So the temperature in Kelvin would be negative 26 plus 273. So that's essentially subtracting that too. And that's going to get us 247 Kelvin in this case. Again, same idea, original number, whole number, converted number here, a whole number. Any questions on any of those there? So obviously you need to be able to convert temperature from Fahrenheit to Celsius, Celsius to Fahrenheit, Celsius to Kelvin, Kelvin to Celsius, Fahrenheit all the way to Kelvin. So any questions on any of those there? Okay. It's good they agree. Here's, again, just some comparisons of our different temperature scales, all pretty much calculated based on what we've been talking about, those different sort of formulas to do that. And like I said, pretty much, outside of this chapter, that Celsius to Kelvin is the one that you're going to use probably 99% of the time in most cases. Obviously, body temperatures that are above 41 degrees Celsius, that's going to be hyperthermic. Hyper basically means more than, right? That's essentially what that means. And it obviously can lead to not such great things. We're obviously going way above our normal body temperature, which is down in this range. So we're finding ourselves at 41 or above. We're in this range, which is not so good, obviously, in that particular case. The opposite would be true if we sort of were in the cold, hypothermia. Hypo means less than, basically. So that's basically less than normal body temperature. So that would put us in this range here, less than 28.5. That drops it way down here. And obviously that's not good either in that particular case. So Again, sometimes hypothermia, hyperthermia. We see in chemistry a lot those two sort of beginning parts of the words, like hyper, again, meaning more than, and hypo, meaning less than, basically. So we do see that a lot in that particular case. So let's take a look at one here. A person with hypothermia has a body temperature of 34.8 degrees Celsius. What is the temperature in Fahrenheit? And to finish it up here for today, also we'll do Kelvin as well, just to make sure. We'll start with the one that's in the question, which is we're going from Celsius to Fahrenheit. So again, temperature in Fahrenheit there will equal 1.8 our temperature in Celsius plus a 32. So 1.8 times 34.8 plus a 32, and that would get us 1.8 times 34.8 plus a 32. Looks like 94.64 is what you get on your calculator. Again, in terms of how we would want to represent the answer, our original number here goes to the first decimal point. So we would want to go to the first decimal point here and take it to 94.6 degrees Fahrenheit. Any questions on that one there? And then to calculate our Kelvin, it is our Celsius plus our 273. So just plugging that in, 34.8 plus a 273. That's going to get us 307.8 Kelvin. And same idea here, goes to 1 decimal place here. We'll take our Kelvin also to 1 decimal place there as well. So again, as we've been talking about, if you're just solely doing a straight temperature to temperature conversion, again, we kind of do a sort of modified rule in terms of significant figures, and it's a very simple one that essentially whatever the original number looks like, make your converted temperature value look exactly the same in terms of how many digits are displayed. So again, whole number, take it to a whole number, 1 decimal place, 1 decimal place, and so forth. Any questions on temperature conversions? And you do need to know how to do these. I'm not sure they will be provided for you, these formulas. So make sure that you know them and star them so you know how to do those conversions. And again, out of all of them, just to reiterate, this guy right here is the one probably the most of the time you will use in chemistry. Any questions on that or anything we talked about here? Okay, so this will probably wrap up most of chapter 3. There's one little part I think left to talk about, and I'm not sure exactly how we would do that. I think I might just record that last part and post it for everybody. So again, on Wednesday during lecture, we will go to chapter 4 with everybody. And those that, again, that had discussion on Wednesday, we'll take care of those guys with the same lecture we just did here, so they're on the same page. But that's sort of the game plan as of now. Any questions on anything? Okay. Other than that, if you're good, I'm good. Make sure you put here if you haven't done so. If you happen to still have questions on something, I'd be happy to answer. Otherwise, have a good night, and I will see you on Wednesday.